talk about inverses, but it's going to be symbolically. We've already talked about inverses graphically, but now we're going to talk about how to find the inverse of the symbolic form of a function. So first of all, let's refresh. When finding the graph of an inverse of a one-to-one function f, if f has the point xy, then f inverse has the point yx, right? Remember, we were swapping our input and output values, right? The main point of an inverse is swapping the input and output values. And if you'll recall, remember we had these sort of opposing representations for f and f inverse, where we could plug x into f and it would give us y, and we could plug y into f inverse and it would actually spit back out x. So we actually end up having a nice sort of loop here. And we can actually think about this in terms of composition, right? Remember, composition is where we plug the output of a function in for the input of another function. Oops. Goes this way. So we have f inverse, and it's giving us x. So if I compose, right, f inverse of f, I get x. Right, remember we work from the inside out, so it's kind of flipped order. So f inverse of f of x, right? We're putting x in, and we get x out. Similarly, if I do the same thing backwards, if I take f of f inverse of x, I get x out as well. So this is a property for inverses that we're going to use. So let's write this down really quickly. For f and its inverse, f inverse, we have first bullet, f inverse of f of x equals x, and f of f inverse of x equals x as well. In other words, f inverse of f of x equals x, and f of f inverse of x equals x. So how can we use this in a problem? Let's say we're given the following example. Is g of x equals x over 2 minus 2 the inverse of f of x equals 2x plus 4? First of all, when we're working on this problem, we really need to check and make sure that we have a one-to-one function. So when we're looking at g and f here, right? One of our first qualifications for us to have an inverse is to be one-to-one. So are these one-to-one? What type of functions are these? Both of these are lines, right? Are lines one-to-one functions? Totally, right? A line that isn't vertical or horizontal, of course, is going to pass both the vertical and horizontal line tests. So these guys are both one-to-one, so we do know that they could have an inverse. In order to use composition to solve this, well, we can use the fact that we just learned. So we know that if they are inverses, then if we compose them, we should just get x out. So let's do that. So let's compose f of g of x. So we know f of g of x by definition is f of g of x. G of x is x over 2 minus 2. So we can replace g of x with what it's equal to. So x over 2 minus 2, right? Again, they're equal. I'm going to do the sort of underlining both of them because they're equal. And now we have something that we're plugging into f. So we've replaced x here with x over 2 minus 2. So we have to replace x here with x over 2 minus 2. So we have 2 times x over 2 minus 2 plus 4. All right, that definitely doesn't look like x, but let's do some simplifying before we make any final decisions. So we have to distribute this 2 to both terms. So we have 2x over 2 minus 4 plus 4. Obviously, the minus 4 and the plus 4 will add together to give us 0, so these guys cancel. Multiplying x by 2 and then dividing x by 2 will sort of undo each other, so these guys also cancel. So we are actually left with just x. So far we know that f composed with g of x, so far we know that f of g of x is x. Let's check the other direction. We always need to check both directions. So now we need to figure out g of f of x. By definition, this is g of f of x. F of x is 2x plus 4, so we have g of 2x plus 4, right? Again, this is equal to this. We're just replacing it with something that it's equal to. So we need to plug this into g, right? G of x is x over 2 minus 2. So g of 2x plus 4 is going to be 2x plus 4 over 2 minus 2. So again, this doesn't look like x necessarily. Let's do some simplification to see what's going on. So we've got 2 in the denominator. That means we need to divide every term by 2 here. So I divide my first term by 2. 2x divided by 2 is just x. Then I have 4 divided by 2, which is 2. And then minus 2. Plus 2 minus 2 zeroes out, so we end up with just x. So in both directions, composing f of g and g of f gives us x. So that means that these two are inverses. Awesome, let's look at another one really quickly. Let's say we're looking at f of x equals x squared plus 3, where x is greater than or equal to 0, and g of x equals square root of x minus 3. All right, we got to do the same thing. We have to compose them. So let's start out here. Let's do f of g of x. So again, that's f of g of x. G of x. Okay, so again, before we start, we want to check and see if these are one-to-one. Well, they're both definitely functions, right? We have a polynomial, quadratic, right? That's a function, and we have a radical function, which is a function. But are they one-to-one? Well, let's think about it. So if we think about this first one, we have a parabola, right? We have that classic U shape, right? And if we're thinking about it, x squared plus 3, it's going to look like this, right? It's going to look like a parabola shifted up 3. Is this one-to-one? Definitely not, right? If we pass any horizontal line through it, any horizontal line above 3, it's going to pass through the function twice. So, but what are we forgetting here when we're just looking at this graph? Well, we had the condition that x is greater than or equal to 0, which means that actually we're just looking at this part of the graph onward, right? These are the x values that are greater than 0. If I'm just looking at this kind of right half of the graph, is it one-to-one? Of course it is, right? Because now this side doesn't matter. So any horizontal line is only going to pass through this side of the graph one time. So this is one-to-one. Is this guy one-to-one? Yeah. Radical functions are one-to-one, right? This is just going to look like this. Any horizontal line passing through there is also going to only pass through the function once. Okay, so now that we know they're both one-to-one, that's our first characteristic that we need to check off in order to have an inverse. So let's continue on here. So f of g of x, we have f of g of x is square root of x minus 3. Then f of square root of x minus 3 means we need to plug this in for x over here. So we have square root of x minus 3 squared plus 3. Square root of something squared is x minus 3 plus 3. Minus 3 and then plus 3 gives us 0, so we're just left with x. So far, we are good. This is very possibly the correct inverse. Okay, what is g of f of x? Well, again, we've got g of f of x. So f of x is x squared plus 3. So we have g of x squared plus 3. G of x squared plus 3 means we have to plug x squared plus 3 in for x over here, so we do that. We have x squared plus 3 minus 3. So again, plus 3 minus 3 is gonna cancel. So we have the square root, right? These guys are gonna cancel. So we have the square root of x squared. Square root of x squared, well, square root is asking us kind of the opposite of squared, so we're just left with x. So both of these give us x, which means that these two functions are inverses. So yes, they're inverses. They're inverses. Let's look at the graphs of these really quick again and just double check with our graphical definition of inverses. Remember, we have the right half of a parabola that's been shifted up 3, right? That's f. And underneath we have a square root function that's been shifted right 3. And remember, our sort of graphical definition of inverses was that they were flipped over the line y equals x. Do these guys look like they've been flipped over the line y equals x? They totally do, so these are great. Right, this is the point 0, 3, and this is the point 3, 0. Right, we've swapped x and y, so this is correct. Okay, so now we've talked about that method of checking whether we have an inverse. Let's talk about how to find an inverse. So finding inverses. Given a one-to-one function f, we always have to remember that one-to-one function part. 1, we want to replace f of x with y. Or if it's g of x or g of t or whatever it is we want to replace with our dependent variable. We want to swap all x's and y's. Right? We want to swap our input and output variables. Then we want to solve for y. And last, we can replace y with our function notation for inverse. So if it was the function f of x, then our inverse notation would be f inverse of x. Okay, let's give this a shot. Okay, find f inverse of f of x equals 3x plus 6. Again, first of all, is this one-to-one? Totally. Again, this is another line, so this is a one-to-one function. Okay, well, we're starting off with 3x plus 6. Our first step is to replace f of x with y, so we can go ahead and write y equals 3x plus 6. All right, next step is to swap our input and output variables. So we swap y becomes x and x becomes y. And now we want to solve for y. So we want to get y by itself. So we start by subtracting 6 from both sides. So we end up with x minus 6 equals 3y. And then last thing we need to do to get y by itself is divide by 3 on both sides. So we end up with y equals x minus 6 divided by 3. So our inverse is f inverse, that's the function notation. And we got x minus 6 divided by 3. And that's the answer. Simple as that. Next question, let's find g inverse of g of x equals x over 3 minus 2. Is this guy one-to-one? This guy is also one-to-one because it, again, is a line. It's got a slope of 1/3 and a y-intercept of -2. So we want to replace function notation with y. So we have y equals x over 3 minus 2. Now we swap our input and output variables, so we end up with x equals y over 3 minus 2. Now we want to solve for y, so we continue. We can add 2 to both sides, so we end up with x plus 2 equals y over 3. And then we multiply by 3 on both sides. So we have y equals 3 times x plus 2. So then g inverse of x is 3 times x plus 2. Is this problem related to this problem in any way? Can we rewrite this function at all? Can we simplify this anymore? If we simplify, we end up with, we distribute the 3, so we have 3x plus 6, which is f. Right? So interesting, we found the inverse of g of x and we got f up here. But is f inverse equal to g? Well, can we rewrite this at all? What if we split up that fraction into two terms? So we divide the first term by 3, so we have x over 3, and then minus 6 divided by 3 is 2. So we did get g. And that's something that's really interesting and kind of important about inverses, is that there's only one inverse for every function. So even if they maybe look a little different algebraically, we can simplify them to look the same. And then when you take the inverse of a function and you get f inverse, and then you take the inverse of that function, right, which we, again, these are equal, so we took the inverse of f inverse, we got back our original function. That should always be the case. All right, let's find f inverse of f of x equals, okay, let's say I have x minus 5 squared. Now, is this guy 1 to 1? 1 to 1 means we pass the horizontal and vertical line test. It's definitely a function, so we pass the vertical line test, but do we pass the horizontal line test? No, quadratics on their own do not pass the horizontal line test. So typically, if you're asked to find a function like this, it will say something like, find the domain where f of x is 1 to 1 and non-decreasing. And then it will ask you to find the inverse. So what does that mean? So first of all, we need to figure out where it's 1 to 1 and then non-decreasing. Well, 1 to 1 was a simple fix, right? If we think back to the example from before where we had a quadratic, we decided to only pick the right half of the function, right? So we just have to do that here. Let's think about this. So our function this time is x minus 5 squared. So now we have negative 5 inside of the parentheses. Inside of the parentheses means horizontal, which means it's going to do kind of the opposite of what we think. So this is going to give us this guy, right? This function is going to look like this. Right, x squared, but shifted to the right 5. Okay, so in order for it to be 1 to 1, we just have to pick part of the function so that we don't have the symmetric side as well. So we want it to be 1 to 1, so we can pick maybe this side or this side. But remember, we want it to be non-decreasing. Non-decreasing sounds kind of like increasing, but sounds kind of like increasing, right? So probably this side. So increasing, increasing, increasing. But what about the 0.50, right? This point right here is 50. Do we want to include that part or not? Well, are we increasing at the 0.50? Well, remember, we can't be increasing or decreasing necessarily at a specific point. But, however, if we include that point, is it going to make it not 1-to-1? No, there's no other point on the graph that passes through the y value of 0. And remember, it also didn't necessarily say increasing, it just said non-decreasing. So if all of this is the part where we're decreasing all the way up to 0 but not including it, then non-decreasing includes that point as well. So our domain here that is 1-to-1 and non-decreasing is 5 to infinity. Okay, 5 to infinity are all of the x values that are greater than or equal to 5. So let's go ahead and start finding the inverse. So our function here is y equals x minus 5 squared with x being greater than or equal to 5. Okay, let's go ahead and start finding the inverse. So we want to swap the input and output values. So we have x equals y minus 5 squared. Is that the only x we have to replace? We also have this x is greater than or equal to 5 tagging along. So here we have y is greater than or equal to 5. I know this doesn't seem like it'll be useful, but it actually will. So let's keep going. All right, so we want to solve for y. In order to get rid of this squared, we need to square root here. So we take the square root of both sides. Use the square root of x. And remember, this is plus or minus equals y minus 5. And then we add 5 over. So we end up with y equals plus or minus the square root of x plus 5. This isn't really ideal for a function, right? Having a plus or minus in there. But we have something that can tip us off as to whether we want positive or negative, right? This guy. We want y to be greater than or equal to 5. Y to be greater than or equal to 5. So if we have this guy, plus 5, and we know we want to be greater than 5, then we want to add something positive to 5. So that means that our final inverse, f inverse of x, is positive square root of x plus 5. That is our answer. If we look at the graph of this, we're starting with x minus 5 squared. That is this guy, right? Half of a parabola that's been shifted to the right by 5. Looks like this. And then our inverse, we have a square root function that's been shifted up 5. So we have this. These guys definitely look like inverses, right? They look like they've been flipped across the line y equals 5. So this is good. Okay. What if we'd asked for non-increasing? Let's try that one. So non-increasing would be the other half of the graph, right? This part was increasing. So the non-increasing part of the graph would be this side. And again, we would still want to include x equals 5 because that part is neither increasing nor decreasing. So that is all the x values up through 5 and including 5, which we can write as x is less than or equal to 5. And then we follow pretty much all the same steps. We swap x and y. And then we solve for y. we take the square root, we get plus or minus square root of x is y minus 5. Then we add 5 over, we get y equals plus or minus square root of x plus 5. We know we want to be less than or equal to 5, so we want to add something negative. So f inverse in this case is negative square root of x plus 5. If we look at this graph, we've got the situation where, again, we have half of a parabola that's been shifted to the right by 5, but it's the left half. And then we have a square root function that's been flipped over the x-axis, so it's downwards, and then it's been shifted up by 5. So we're actually looking kind of like this, right? This has also been swapped over the line y equals x, so we are good. Okay, I want to do one more type of function because it's kind of a tricky one that you'll see potentially in WebAssign. So let's say you're given f of x equals x over x plus 4. Why is this different from what we've looked at before? Well, it has two x's, right? All the other functions we've looked at have just had one x. So this is a little bit different, but not super scary. We can just follow our normal process. First of all, we want to check whether it's one-to-one. This is a much more difficult function to see whether we have a one-to-one function. But if we graph it, we end up with something that looks like this, which we can see from it gives us a one-to-one function. If you were given this problem on a test or something, I would go ahead and tell you that it was a one-to-one function. So let's go ahead and start our process. So we replace f of x with y. So we have an input and an output variable. Then we swap our input and output variables. So we have x equals y over y plus 4. Now this is why it's more tricky to deal with two x values than to deal with one, because now we have to get y by itself, but there's two of them. Seems like it might be kind of impossible, but it's actually not. So let's give this a shot. First of all, our best hope of doing this is going to be to get y out of the denominator. So how can we do that? How do we normally get rid of a denominator? Well, we multiply both sides by whatever it is, right? So if I multiply both sides by the denominator, y plus 4, I have x times y plus 4 equals y over y plus 4. I'm going to write the whole thing out so we can really see what's going on. So I multiply both sides by y plus 4. The denominator, right, the division and the multiplication kind of undo each other. So we're left with x times y plus 4 equals just y. Okay, so we want to get the y's on one side together. So how can we do that? Well, we definitely need to get the y out of this whole situation where it's being multiplied and added and all this stuff. So let's distribute x here so that we can move that term around. So we have xy plus 4x equals y. Then we subtract, bring this xy term over to the other side by subtracting by xy on both sides. So we're left with 4x equals y minus xy. Now this looks pretty funky, but, or how can we separate y from the rest of this stuff? Well, we have two terms here with a y in each. When we have that, in the past we've just factored. right? We can factor a y out here. So we have 4x equals y times what's left if I divide by y in that first term? Just 1. And then minus what's left if I divide by y here? Just x, right? So now I have y times something is equal to 4x. How do I get y by itself? Well, I just divide by whatever it is, right? If I'm multiplying, then I just divide to undo it. So I have 4x divided by 1 minus x equals y. And my very last step is to write it in function notation form. So we started with f of x. So now we have f inverse of x equals 4x over 1 minus x. This is my answer. Okay, y'all. Hopefully this finding inverses symbolically is making sense, and we can kind of see how it relates back to finding inverses graphically. And that's all I have for y'all today. Thanks, y'all.